Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are in our final chapter, and in this chapter we have already discussed quantum memories. Just to briefly recap those ideas, we want to work with qubits for using qubits for quantum information processing, but there is a problem of decoherence. And what we saw in the last lecture was that you can put a lot of qubits together and create states which have degeneracy associated with qubits, but that degeneracy is not protected by any symmetry. And an example of this is the Z2 gates theory. And we looked at examples defined on a torus, and we found that it has a degeneracy of 4. We went on to look at the statistical mechanics of a classical version of this gates theory, and this is a model with local symmetry. And the important concept that we learnt in the last lecture was the idea of Elitsur theorem, which says that a local symmetry cannot be broken. In other words, you should only look at those observables which are gauge invariant, in the sense that anything that transforms non-trivially under the local symmetry should not be used as an observable. And we found a very nice class of observables which are indeed gauge invariant, and these are called Wilson loops. And we saw that if the toric code that we discussed, the classical version of that has what is called as area law phase at any finite temperature, and the 0 temperature phase is not area law, and that is the 0 temperature phase is the one that has all the interesting topological properties. Now if you put the same theory in a higher dimension, like for example if you put that in a theory on the 3-dimensional cubic lattice, then you will see that there is actually a phase transition. There is a low temperature phase which is not area law, and a high temperature phase which is area law, and there is actually a continuous phase transition. So you actually have an example of a system where you do not have a symmetry breaking, but yet there is a phase transition. So this is also a very interesting phenomena. So we have seen examples of applications of statistical physics to such problems. Today we will look at something far more topical and even very commonly discussed in the general literature and even press and newspapers, etc. And this is the idea of neural networks and artificial intelligence. And here too you will see that statistical mechanics can be a very useful tool. And what we are going to discuss today is just again to whet your appetite to explore further. We are going to discuss what are called as associative memories, and I will show you that the kind of models that we discussed in this course will be useful in understanding ideas and formulating problems in the area of neural networks and artificial intelligence. So the central question that we are going to discuss in this lecture is try to build a very crude model, I do not know crude, but maybe a decent model that can describe how our brain stores information and how we recall it. Okay. So this is called as the Hopfield model, and it is related to neural networks and machine learning, etc. So I will show you this in this lecture. So let us start by stating the problem. So you can see that I have here a picture here, and suppose I ask you whose picture is this. You might want to pause the video and take a quick look and answer this question. And I am sure that you know that this is Mahatma Gandhiji's picture. And the remarkable thing is that this picture has very few details. There is just the characteristic rimmed spectacles and just the outline, and yet we are able to make an identification that it is a picture of Mahatma Gandhiji. So how did we make this identification with no details, right? So you see, right from childhood we have seen many pictures of Mahatma Gandhiji, etc., and our brain has stored that information in some way. And when this stimulus, when you are watching this lecture and when you see this picture on the screen, it stimulates your brain and the brain then reconstructs, if you wish, this idea of Mahatma Gandhi's picture. So this information of this picture is actually somehow stored in your brain in some way, and the way we understand it today is that there are a lot of neurons, these are the nerve cells if you wish, and these neurons are connected to each other by what are called synapses. I am not going to get into the biology of this, just some words. And the information is actually stored in these synapses. It is somehow stored in the strength of these connections between the neurons. So the strength of the connections is where the information is stored. So this is all very interesting, and I am sure you have seen this in high school biology and so on. But the question is, how does the brain retrieve this information, and can we make a simple model of this? And I am going to try to impress upon you that the Ising kind of model that we have discussed in this course can actually capture some of this, some of these ideas, right? Some of these concepts that we have seen in the context of brain memory and recollection and all of that. We can build a model using something like an Ising model to actually get an idea of how this could possibly be happening. So it is really a model in the sense that there is some reality of what is going on in the brain, and we are constructing a model that sort of captures this idea. Okay. So what are we going to do? So what I am going to show, what I am showing you here is, first we have to get an idea of what do we mean by an image, and how can we make the idea of an image a little bit quantitative. So what we are going to do is, we are going to imagine that the image is made of lots of pixels if you wish, and let us just think of some 2 colored images, not very complicated things like what we have seen before, right. So you can imagine that an image is a set of n Ising spins labeled by I going from 1 to n, and so for example in this image you have some red pixels and some black pixels, etc. So you can imagine them to be spins sitting at the centers of these little squares, right. So this is a 16 by 16 grid, and whenever the color is red, that means that the spin there is in the up state or the +1 state, and when it is black it is in the -1 state. Now if you want to construct image on the 16 by 16 grid, there are 2 power n possible images with this coloring scheme, and there are lots of images, that is what I am trying to point out, and some of them look random to you in the sense that they do not seem to have any sort of discernible information or something like that. But something like this has a pattern in it, right. So this has some kind of pattern, some kind of QR code kind of stuff here, there is some pattern sitting here. And the question is, how can I memorize these patterns? That is, suppose I give you m such patterns, how can I memorize them? So what I have shown you here is, how can you map the image to spins, right? And some of those images may be completely random, so there will be some kind of random spin configuration, and this configuration has some kind of order for us in the sense that we see, oh, this is some kind of nice and symmetric pattern, right. Okay. So I want to take a bunch of these patterns and I want to create a memory, which means that whatever I am going to create has information associated with this pattern stored in them, right. This is what we mean by memory. So suppose I have m patterns, and in the example I am going to show you, there are 8 patterns, each of them are 16 by 16 patterns. So that means there are 256 spins, and I tell you the configurations of the spins, and none of these are purely random patterns in the sense that they have some symmetry and there are some, so we sort of believe that so this could mean that if this is some QR code of some object you are purchasing, so this could mean apple, orange, or variety of vegetables and fruits. Each of these could mean the code associated with that, with a fruit or vegetable. So you have these 8 patterns, and what I want to do is I want to memorize them, I want to remember them. So each pattern, like I said, alpha going from 1 to 8, there are 8 patterns, is described by a special set of spin configuration which I call C alpha I, alpha going from 1 to n. So this is the configuration of the memory, each pattern, right, and so on. Just a small caveat, the way I am going to construct this is, if I have the negative of this pattern, that means that if I change the red to blue and blue to red, so that is like going from m alpha to minus m alpha if you wish. So I change C alpha I to minus C alpha I. We identify these 2 patterns. That is, we do not see whether the picture is positive or negative in the photographic language. We just want the information that is there in the picture in terms of the relative black difference of colors. So this is not a critical thing, it is just that it will show up in our model. Now what I am going to do is I am going to claim that memorizing this 8 patterns is equivalent to defining an Ising model in the following sense. So you see, I have n spins which are n going from 1 to 256 in this case, and I am going to construct exchange coupling constants between them, between every 2 spins. So in this model of Ising spins, every spin interacts with everything else. So for example, this spin will interact with this will interact with that, it will all interact with everyone else. And how do I construct this coupling constants? So you take the patterns that you want to memorize, and you construct this outer product of these patterns, right? Outer product in the spin coordinate, so I and j. So you take the I component and the j component, the spin at the ith side and the spin at the jth side, multiply them and sum over all the different patterns and divide it by the number of spins. That quantity is the exchange coupling constant between these 2 spins. Okay. So given these patterns that you have memorized, these Jij get defined by the patterns that you have memorized. Now you give me any other image, so that image could be this C, this is some arbitrary configuration of spin, this may or may not be related to any of these patterns. I can define a Hamiltonian or an energy associated with that, that is simply Jij Sij with a minus 1/2 here. Minus 1/2 because here I am running over unrestricted sums over I and j, we are not looking at nearest neighbor, anything like that, and we are letting I go from 1 to n, j go from 1 to n, and we just write this out, and this is the Hamiltonian. So this model is called as the Hopfield model. It was extensively explored by Hopfield in the early stages of this field. Okay, so this is the idea. Now I am going to show you that the Hopfield model can serve as a memory. Okay, so now so far we have thought of the spins as representing a picture, right? So we are imagining that we are taking a picture, pixelating it, and then there is the black or white or red or blue in our case, and we are just coloring it, and that's the picture. So to make a memory which can remember things and recall things, we are now going to make a further connection or a further mapping. So these pixels that we have, which are black and white, they can also be thought of as the states of neurons when this image is shown to the brain. So what that means is, if the picture has if one of the picture pixels has white in it, it means that the neuron to which this pixel is fed, that will be in some state, as opposed to when it is black or blue, it will be in another state. So the idea is that this image can be mapped to some state of the neurons. So the +1 state of the spin is like the active state of the neuron, and the -1 state of the spin is the passive state of the neuron. So what we are doing is, in this Ising model, we are sort of now thinking that the spins are also states of neurons. The state of the spin is like state of the neuron. So when you give me an image, you map it to the spins, and that will initiate the initial state of the collection of neurons, these spins, the Ising spins. Okay? If you think of this as like a neural network, if you think of these spins as neurons, then in the neural network language, these JIJs are conventionally called as the weights between connecting the neurons, and these are the strengths of the synapses. Now I had mentioned a couple of slides back that the memory is stored in the strengths of the synapses, and this is exactly what we are now seeing, that these JIJs, which were actually developed by looking at each of the pattern and finding the outer product of them and summing over them, this is how the couplings are the ones that encode the patterns that are to be remembered. Okay. Now to connect further with the neural network language, so typically a neural network has to be trained. So neural network has some input data, and then there is an output data, there could be many layers and so on. So there are these neurons in each layer, and there are connections between them which are the weights, and they have to be trained to achieve certain purpose. So if you want to identify variety of objects, you have to feed them a lot of these objects and have some label classifying each one of them, and train the network so that the weights are correctly determined, so that at least the ones that you fed in, it reproduces the data correctly. It identifies the images correctly, let us say. That is called as training. In our case, this process of identifying Jij with this quantity, which is setting the weights Wij, is the training process, right. So what we call as memorization, so Jij was, we were creating synapses by looking at the patterns themselves. This is the training in this Hopfield network. So once you tell me the patterns, the network is automatically trained by this construction, right. So now we have training. Now what is the use of this? So I have created some network, and I have these weights which are Jij, or the exchange couplings in the Ising language. What do I do with it? So now the question is, I am going to use this network to identify an unknown image. So someone gives me an image, and they ask me which, and it could be noisy, which of these patterns does this picture correspond to? Right, this image, which of these patterns does it correspond to? So I am going to show you that we can use this Hopfield neural network to actually recognize or recall which pattern that a given image corresponds to, and that image may not be exactly the pattern that you started off with, it could be something with noise, etc. Okay. Now I am going to show you that this is done dynamically. So what do? You start with initialize the neurons, that is the spins, in the state corresponding to the image that is given to you, and that is this configuration C, which is the set of spins that you are going to do. This is the image that you are giving me. This may or may not be one of the patterns that has been memorized. So you initialize this. Once you are initialized, there is going to be something like a dynamics, that is, there is going to be some steps taken, just like Monte Carlo steps if you wish, right. And what you do, you have to repeat the following steps a large number of times. And what is that large number? Do not worry about it now, you can do your own calculations and see for your system how many steps are required. You will just see this yourself, right. And what you have to do for large number of times is the following: pick a spin in this configuration at random. and using the configuration of all other spins, you find the effective magnetic field on the spin that you have chosen. So that is very straightforwardly seen. We have seen this is like something when we were doing mean field theory, we understood that this is the effective magnetic field acting on the spin I. So you just run over all the j's which are not I, and you just take the exchange couplings, multiply them by the spin state at all the j's, and you will get the hi. And the dynamics you are going to do is the following: you will find this hi and make sure that the spin Si points in the same direction as Hi. So if Hi is positive, the spin will be plus 1, if Hi is negative, the spin will be minus 1. Okay? And so you keep doing this, and what you will find is after sufficient number of steps, you will see that the configurations will not change. The configuration will go to some what is called as a fixed point of this dynamics, right? Some kind of equilibrium state of this dynamics. Right, and this is the statement here, it will reach a fixed point. Okay, so this is what happens, and this is, and my claim is that fixed point will be one of the patterns that you had memorized, right. Magically, this is what I say, is that the fixed point will turn out to be one of the memorized patterns. So let us see this in action. Okay. So what I do is, you see I had stored 8 images and I take one of them, so I can just quickly show you which one I am taking. So you see I think it is this one here, the last one. I take that image and I add some noise to it. So I take this image and I add some noise to it, and it does not look anything like the image that you started, it has no symmetry, nothing. And then I run it through this Hopfield network by precisely the algorithm that I had told you, and I recover this exact image, right. I took this image, I distorted it significantly, in fact 30% of the pixels were changed here, and it comes back, it recovers that image. So you may think, oh, this is a fluke because I started with this one. Well, I started with another one too, and I 30% distorted it, and you can see that it is completely, it looks absolutely nothing like this. A human, when they look at this, cannot see that it is a distorted version, at least this human cannot. Right, so you see, and then you run this Hopfield and you recover this back exactly. So it is able to correctly identify the pattern, and how does this happen, right? So what is the physics behind this, and how are the set of Ising interactions help it to identify these images? So if you have not seen this before, I think it may be a good idea for you to pause the video and just think about this, how this could actually possibly work. It is an interesting exercise, and if you find something, it will be also quite exciting for you. Okay, let me proceed. So the whole game in the Hopfield model, now we look at the Hopfield model from a very physics perspective. We say that every image has an energy, and this is just the Hamiltonian associated image. This is what we defined. And the way I defined Jij, it will take a little bit of algebra, it is not too difficult, you can just figure it out yourself, that this term can be re-expressed as the following. You look at sum over patterns, and what is this quantity? This quantity can be thought of as some kind of inner product between the image that you have and the pattern that is remembered. So this whole expression can be sort of, the energy associated with an image is the sum square of the projections of those images on the patterns that you have, right. So you can see that this energy will be minimized whenever a pattern is completely equal to like one of the images that you have, right. So this will become like a very large number, it will be like proportional to n and so on, and then you will see that it will square, and so the energy will be proportional to n and so on, negative n, that is. So you will see that all these images are so you will see that there is an energy minimization idea here. So to proceed further, I am not going to go too much into the math of this. There is a lot of literature on this, but I will just try to stay a little bit qualitative. So let us make a reasonable assumption that all the patterns are significantly different from each other. And what I mean by that is that if you take the inner product of any two patterns that are remembered, the 8 patterns we had, if you take any of 2 of them and take an inner product like something like this, I am taking the sum over products of the components at each spin site and then adding them up, I am going to assume that that result is going to be fairly small. So in some sense I am assuming that each pattern is kind of orthogonal to the other, right. If you do that, then you can make a very clear argument here. You will be able to see that each of the patterns is actually a local energy minimum of this energy function. That means if instead of the C, instead of an arbitrary image, if I feed the pattern itself, you will get some energy, you will get some negative of energy, right. You will get some energy, and that energy is a local minimum. What do I mean by local minimum? That means that if I take the energy associated with this and simply change the pattern M alpha, the pattern associated with the mth memory pattern, if I flip one single spin, then you will see that the energy will increase. That means that it is a local minimum. So the remarkable thing is that this Hamiltonian has all these local minima. So for example, I have this memory of 8 patterns which I am numbering from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7, and they all have energies which are some negative of that. By the way, this the energy here for practical some computational reasons is taken to be 2 times this, so that we do not need to worry about this half. Right, and so this is the plot that is shown here, and you see that they are roughly somewhere in this ballpark, somewhere between, they are close to n if you wish, right. N is the number of sites, number of Ising spins, right. So that is the kind of numbers you get, and they are all local minima, right. So this is just a schematic plot, so you can imagine this to be some configuration space, and there are all these local minima associated with it. So if you go away from here, the energy will sort of increase. Say for example, if I change the pattern here, the energy will sort of go up around this local minimum. Okay. So how does our algorithm help us? So what the algorithm does is, you think about what the Ising model is. The Ising model is the Ising interaction between the different spins will effectively can be thought of as, I have all this others, if I look at a spin I, there are the other spins are in their own configuration, and what do the other spins do to the spin? So there is some effective magnetic field, that is the one that we showed here, this one, at the spin I. So if you now change the spin at site I to point in the same direction as the magnetic field coming from the other spins, then of course you will reduce the energy. And this is exactly what happens. So I start with some some high energy compared to this state here, and then I just keep coming down, and lo and behold it becomes stationary, the energy stops decreasing, and you actually recover one of the images that you start off with, right. So this is another way of showing. So you started off with this high energy state, and it will the low energy, this value will turn out to be the energy of this pattern. So now you see the remarkable dynamics that we have cooked up for this recognition or recall is simply energy minimization. It is a way of doing steps to minimize energy. If you can even think of this like some kind of Monte Carlo kind of thing, where you are not using temperature, you are just going downhill in energy. In Monte Carlo, of course, you are also allowed to go up in energy, and by the way, there are versions of this Hopfield idea which also uses a notion of temperature, etc. I will mention very briefly as we go along. But what we have managed to see is that we have managed to show, based on this idea, that recall of a pattern is simply energy minimization. So this is a very nice idea, because we understand a lot about the physics of spin systems, etc., and we know how to minimize energy there and so on. So this is one of the very nice connections between neural networks and say statistical physics. So now this is very exciting. We can our memory works well. I have tried please try to write your own program and check this out. You can also use many standard packages for this if you wish. Now if you play around with this, the kind of setup that I had 8 patterns that I remembered, and the total number of spins I had was 256. Now the question is, with 256 spins, how many patterns can I remember and I can recall well? Of course I can put any number of patterns, I can get JIJs, that's not difficult, training is not difficult, but the question is, does this memory work reliably, and so on. So this was a question that was asked very early on in this in this area, and Hopfield and many related works went on to show that the capacity of such a network, capacity means what is the maximum number of patterns it can remember reliably. Reliably you can say 99% of times it should get some pattern that is that you have remembered. So it turns out that the maximum number of patterns it can remember is something like 0.14, it is like 14% of the number of spins. So if you exceed this, then it can just do some random things and it can it will not be a reliable memory. So that is the capacity. Okay. Now why is there a capacity, and why is it that you can only store a finite number of patterns and you can recall them well? So the important thing to understand is, as we saw after some number of steps there is something like some exponential decrease of energy as a function of steps, and then the energy stops decreasing and it remains stable. What this means is that it remains fixed. What this means is that the pattern that is reached after all those steps, or the image that is reached after all those steps, is actually a fixed point of the dynamics. It is something like an equilibrium state of the dynamics that we have developed, this finding the magnetic field and changing the direction of the spin along that direction. And certainly we know that the patterns that were memorized, we certainly want them to be fixed point of dynamics, because then you will go to those fixed points which are the patterns that you have memorized. So in particular you can ask, under what condition is this equation always satisfied, even if there are some small perturbations around this initial pattern, right? Now what you will realize is, suppose you memorize some number of patterns, you will find that in the Hopfield model there will be other patterns which you have not memorized which are also fixed points of this equation. So in addition to the patterns that you have memorized, there will be other images which are fixed point patterns. This is a remarkable thing, and let me show it to you. So what I do is, I take a Hopfield memory, I construct a Hopfield memory with memorizing 16 patterns now, double of the patterns that I had in the same 16 by 16 or 256 qubits. So there are these 16 patterns which I have memorized. Okay, so I have defined my Jij etc. using these 16 patterns. Okay. So now you will see that there is a perfect recall for a certain images. So for example, I feed it, I take this pattern, I put in noise and I run through the Hopfield network, the dynamics, and then I recover exactly this image, it's exact overlap, same energy and so on, I get this. But now you will see something very interesting. Take this particular pattern which is a memorized pattern and you add noise to it, it goes to a pattern. Now you can see that this pattern more or less looks like the pattern that we start off with, but it is not exactly the same pattern. So for example, I can show you one difference here. So, you look at this here, this is dark and that this is blue and that is red, but if you look at the same thing here, there is no, this is still red. So, there are a few bits of difference between these, but you see the energy of this also continues, you know, once this dynamic settles in, the energy will not change, it will be the energy of this pattern, and that is also a local minimum, right. So, there are several other bits that different, say for example this one and so on, and there is some structural difference here, there are many differences. So, these are not separated by single qubits, single bits, there are several differences of these, yet this is also some local energy minimum. So, this is a remarkable phenomena that you set in these Jij objects, and in addition to the states that you thought were minima, it is producing new states that are minima, right. So, this is a very intriguing and very sort of puzzling feature here. So, it turns out that this problem of if you say memory or retrieval and all of this stuff that was done in neural networks has some very deep connections to a class of problems in statistical physics called as spin glasses. So, you can see that this is a segue for me to just again introduce you to the idea of spin glasses. Of course, I have just one transparency, it does absolutely no justice to the massively big area of spin glasses, but I hope you will get some idea. So, let us just discuss the standard Ising model where I have some nice translational invariant local coupling. So, for example, I have a spin at a site, I have a square lattice spin at a site just talks to its neighbors and so on, and then you know so when you cool it down, if you are in sufficiently high dimensions like 2, then you will break symmetry and you will go to some ordered phase and you get a ferromagnet and so on. Now, imagine that I have a system where these J's are not, you know, there is no translational symmetry or per se in the problem, and these J's are kind of random. And remember, if I have completely random signed interactions or I have some lattice with some interesting structure, then I can actually have frustration. Frustration is a situation where there are multiple configurations with same energy and the system does not know which one to choose. So, in such systems you can get a very new kind of phase, I want to call this, of these spins, and this is called as the spin glass phase. Now, what is a spin glass phase? Let me try to explain qualitatively to you. So, I am at a very high temperature corresponding to let us say any of the coupling constants in my problem, and then I will just have the paramagnetic phase. No, each spin, the entropy wins and each spin is doing its own thing and I have the standard paramagnet. But now I have all these random couplings, let us say, and I cool down the system. Now, when I cool down the system, what will happen is, if I go sufficiently below certain temperature, which is called the critical temperature, you will see that the spins will start off sort of lock in certain orientation at different sites. So, they will get locked there and you will see that every spin is frozen in some random state, and the random state because you know the couplings are random. So, if you look at say the expectation value of the spins at any site, then it will pick up some non-zero expectation value because it may be fluctuating, but most of the time it will be pointing in a certain either the up or down direction, let us say up direction. So, you will get a non-zero positive value of expectation value of Si, right. But if you average over all the spins this Si, you will get zero magnetization. So, the idea is that if you probe magnetization on the average, if you find the total magnetization of the sample, let us say you do a probe on a very large scale, then you will find it has no magnetization. But if you probe on a small scale like on the atomic scale, on the lattice scale, then you will see that there is some kind of magnetization forming. So, it is like random magnetization, positive, negative, something that forms, and then this will average out to 0. So, this is a peculiar state. So, there is symmetry broken? Well, if you take a sample, yes, it is broken because the state is not but does it have some magnetization? No, then it does not. So this is the state which we call as a spin glass state. Now remarkably, if you give me some state here, I sort of heat it up, I go above this critical temperature and I go to the paramagnetic phase, I bring it back, it will not come back to the same state, it will go to some other state, but which has essentially the same statistical properties if you wish, right. So this is the phenomena, and a standard model to study this, there is something called the Edwards-Anderson model, which has these J's which are plus 1 or minus 1, or there is something called the Sherrington-Kirkpatrick model, is called the SK model in the field, and it is again Ising spins and they all interact with each other, and if these Jij's are Gaussian, then it is this SK model. So what we know from the physics of SK model, I will just qualitatively tell you what happens here, is that if you are at temperatures much higher than this standard deviation of this Gaussian, which I call just J without any symbol here, I and J, then the system will be in a paramagnetic state. But below some critical temperature, in the usual Landau theory of the ferromagnetic, you will get these two minima. But here what will happen is, there will be multiple local minima that form when you cool down the system. So if you cool down the system, let us say this Tc were something, let us say 1 in some units, then if you come to 0.9, there will be more minima. So just below Tc, let us say you are 2 minima, then those minima will split, and as you keep going down in temperature, the minimas will keep splitting further, and if you go very far down temperature, there will be a very large number of minima that are there, and all of these have essentially the same physics in the sense that if you look at statistical properties within one of these minima, they look roughly the same, but they are different in the sense that you can see that they are different if you examine them. So this is quite similar to what is happening in the Hopfield model, right. So this is the extra local minima that we are finding. So once you put in the Jij, the Jij's are random in some sense because the patterns that I put in were random. So it creates these random couplings, and this gives rise to some kind of spin glass like physics in the Hopfield model. Okay. So you can see that there are some very nice connections between this neural networks and the physics of spin glasses and so on. Okay. So these are some of the ideas that I wanted to sort of introduce you to, and I am sure that you find all these things quite interesting to explore further by yourself. So we have used the Ising model, Ising like model to construct a memory, and we used the idea of using spins as proxies for neurons, and the states of neurons can be mapped to states of spins, and the exchange coupling as synaptic connections, and so we made in a sense a model of the brain, and this is the Hopfield model. So the Hopfield model is a very special kind of neural network where the training is actually straightforward, the training is directly coming from the patterns. This is certainly not the case in general neural networks. You have to train them and it takes a lot of effort to train them. And within this framework of the Hopfield framework, recognizing or retrieval of a memory is essentially energy minimization. Like I mentioned while we were discussing things at the point, there are more general versions of this introducing temperature etc., and something like Monte Carlo can also be applied here. I will not discuss that here. But what I would like to tell you is that this area that has been emerging has lots of connections to many different statistical physics problems. In fact, it has connection to error correction, classical quantum, it has connections to all the different kinds of error correction. I have not discussed that here. And more generally, the area of neural networks and artificial intelligence if you really think deeply about them, they actually pose very interesting physics questions. We can think of a neural network or a large language model or any of these things as a physics system with some set of rules, etc. And we can ask, we can try to bring in ideas of statistical physics, all the different concepts that we have learned in this course, to try and analyze what's going on in the systems and why they are successful in the way they are. They are able to write your essays and so on. So why that happens? This is a very interesting and emerging area, and there is a lot of things to be discovered here. Okay, so that is what I would like to say about these associative memories and so on. So in this last chapter we have discussed quantum memories and some of these associative memories, and I hope you will find some things here that is worth remembering. And let me conclude by thanking you for going through this course, and I hope to see you in a future course. Thank you very much.